Okay, now I want to introduce the Fourier transform. So if you look at the formula, it looks very similar to the Laplace transform, right? The Laplace transform has negative Sx, or negative St, so instead of I, it has negative. And the integration is not from negative infinity to infinity, but it's from 0 to infinity. By the way, there's another Laplace transform where you do go from negative to infinity. It's also called Laplace transform, but that's defined for very special case. So we don't use that often. All right, so something that you realize is it looks very similar to Laplace transform, only that instead of a negative, you're putting an I there. And hopefully that's not going to freak you out because we already know the Euler identity, right? So this is really cosine something plus I times sine something. That's when you're multiplying. This exponential function really doesn't go to infinity or negative infinity. It just fluctuates between two values, right? For a fixed value of s, it just fluctuates between two things. So if you have the function of f of x, let's say the condition of f of x is decaying to 0 and infinity, then you would expect that this integral would be defined. Okay? Now, something that you would learn in mathematical analysis is that it's actually true that whatever function f of x is, if its square integral from negative infinity to infinity is finite, then you can define this. Okay. Yeah. All right. And instead of using f, since it's hard to write in the Laplace transform L, people just write this down. Now,
is there one for Laplace transform?
No, we only use this hat for Fourier transform. Yeah. Now, in the case when the function is not defined from negative infinity to infinity, but it's only defined on an interval, right? Then you can think of that function to have 0 outside the interval, right? Then this formula also looks very much like the Fourier series, right? Except that there should be some normalizing thing outside, right? So in computer science, where no functions are defined from negative infinity to infinity, people just say what we call the regular Fourier series as the Fourier transform. So often you hear something like FFT, fast Fourier transform in computer science. They really mean the Fourier series, not the Fourier transform. Yeah. All right. Now, I said that defining the inversion of the Laplace transform is really hard. On the other hand, the Fourier transform actually has a closed formula that can be calculated to do the inversion. So the inverse Laplace transform of this something that's already Laplace transformed. Oh, let's call that. Yeah. Sometimes people put the hat only on this side. And of course, there's a symbol for that one, which is the upside down. This one is defined as 1 over 2 pi, integral from negative infinity to infinity. And then it's f hat s, now multiplied by e to the negative I sx. And this thing will give you the original f of x back. See, it's a big, now to integrate by s. So if I integrate by s, now it's a function of x, right? So it gives you back your original function. Now I actually want to prove this today because it's often just said, not proved, and it's a bit fun to look at the proof. Now, there's some other conventions. Sometimes people put 1 over square root of 2 pi here, so that the inversion will just have 1 over square root of 2 pi. That makes the Fourier transform and its inversion look very similar to each other. Okay? But we'll follow this one. Okay. Some other things, properties, is that number 1, your Fourier transform is linear. Just like Laplace transform being linear, you can take the transform term by term. Okay. Number 2, if you take the Fourier transform of, or if you take the Fourier transform of f prime of x, well, the proof of this basically copies the Laplace transform proof. Just like how if you have negative s of x, e to the negative st, the derivative by the use of integration by parts, it brings down an s, right? In our case, it brings out a negative is of fx. And by the way, if you do a transform, it's a function of s, right? So I'm putting a head over here, but the result will be a function of s. The proof is exactly the same as how I did it for Laplace transforms. The only difference is at some point this part becomes differentiated, and when that gets differentiated, this is comes down, and then at some point minus appears. So that's funny. Oh, but why do you want this? We like this, right? Why? We like this property. Why?
We don't need to integral.
Huh?
We don't need to integral.
No. Oh, come on. I thought that you understood. What happens to derivatives if you do Fourier transform? It becomes multiplication by something. So if you take a differential equation and you do Fourier transform, the derivatives go away. So you can see that what my plan is to use this to solve the heat equation again. Okay? But the result will be that the heat equation, one of the derivatives will go away, and now you just have ODE. Okay? That's our plan. Now we will also need this, if you have product of 2 Fourier transforms, and if you do the inversion, it's very similar, right? And this is going to give you f of x, convolution with g of x. Now I explained that convolutions, actually, in the literature, there are 2 convolutions, right? If the function is only defined for positives, the integration is done from 0 to x, right? But if the function is defined for negative infinity to positive infinity, then the integration has to be done from negative infinity to infinity. So the formula here is not the version that goes from 0 to x, it's actually from negative infinity to infinity, where one side is f of x. Yeah, I knew something was wrong, sorry. F of s, g of x minus s ds. Okay. That's the convolution, right? All right, so, and you might as well write this as your 4th property. These are some properties, and before we move on to use this for the heat equation, I want to prove this one.